So we've already talked about data preparation and compression in chapters 1 through 4, and then in chapters 5 through 7 we talked a little bit about learning. And so now we're getting into control, robust control. That's going to be, I think, chapter 8. So let's get down here. We can talk a little bit about chapter 8. Here we go, robust control and frequency domain techniques, and together with the master law. So let's just jump right into it. Every control system is built on a model. A model is a mathematical description of the plant that's being controlled. And every model is wrong. At least it's wrong to some degree. The model might be wrong because it was derived from first principles with simplifying assumptions, and those assumptions break down in practice. It might be wrong because it was learned from data and the data were noisy, or the data were insufficient in some way. And it might be wrong because the plant changes over time. The components are going to wear out. The temperatures are going to drift. The operating conditions are going to shift. And it might be wrong in ways that are predictable and structured, or it's going to be wrong in ways that are essentially random and unpredictable. Now, the field of robust control is dedicated to a single question. How can we design a controller that works well, not just for the normal model, not just for the nominal conditions, but for an entire family of models? Think of every possible plant that is consistent with what you know and what you don't know. A robust controller is one it's going to maintain stability and it's going to maintain acceptable performance even when the plant differs from the model by as much as the uncertainty budget allows it to do so. Before discussing robust control synthesis, it's going to help us if we understand the frequency domain perspective that underlies much of the field of control theoretical systems. Instead of thinking about a system's behavior as a time series, like how does the output evolve from moment to moment, frequency domain analysis thinks differently. It thinks about how the system responds to oscillatory inputs of different frequencies. So again, frequency domain techniques. Think of every input signal. It can be decomposed into a sinusoidal component of a different frequency. You were using a mathematical operation called the Fourier transform. Now, we're not new to the Fourier transform. We've talked about it before when we're dealing with FFT for converting pixel signals into frequency signals instead. And the system's transfer function, called g of j omega, where omega is the angular frequency, it will describe for each frequency how much the output is amplified and how much it is phase shifted relative to the input. Now, at frequencies where the system has a large gain, small input oscillations produce large output oscillations. And at frequencies where the gain is small, then the inputs are attenuated. At the resonant frequencies of mechanical systems, of fluids, of electrical circuits, the gain can become extremely large. And that's the phenomenon of resonance. And resonance is one of the engineer's primary concerns. Resonance is not your friend. Now, within the Master framework, the transfer function is computed from the reduced linearized operators, the reduced state matrix, input matrix, and output matrix that emerge from the geometry-aware model reduction pipeline. Those are the reduced linearized operators, and that's going to supply our transfer function. These reduced operators, they inherit the Port-Hamilton structure, which guarantees that the transfer function will have the right physical properties. It's going to have passivity. The system can't spontaneously generate energy. It's going to have stability, such that outputs don't grow without bounded inputs. And it's also going to have the correct interconnection behavior when multiple systems are assembled together. One of the most distinctive features of the Master Law framework is the way it assembles and tracks the total uncertainty budget for the control design. The budget has three sources, and the framework keeps an explicit account of all three. The first source is a truncation error, and that's, as we've discussed previously, that's the mismatch between the full order plant and the reduced model. that results from discarding the high frequency, low energy modes in the model reduction step. The contribution to the uncertainty budget from truncation is measured by summing the squared singular values of all the discarded modes, plus an additional uncertainty from process noise that flows through those discarded directions. The second source is the identification uncertainty, the sigma ID covariance that quantifies how uncertain we are about the learned operators, whether they came from DMD, from SINDI, from regression, from neural network training, whatever. And then the third source might be direct measurement noise or unmodeled dynamics that are known to be present, but they're not explicitly modeled. So those are the three main sources of truncation error. Now all three contributions are added together to form the total uncertainty budget. And this budget is expressed as a bound on how far the plant's true transfer function can deviate from the model's transfer function at each frequency. The robust control synthesis then uses this frequency-dependent uncertainty bound to design a controller that guarantees stability and performance for every plant within the budget. The most widely used robust control synthesis technique in this framework is called mixed sensitivity H-infinity synthesis. So mixed sensitivity H-infinity. Now the name sounds technical, but the underlying idea is pretty intuitive. You simply want a controller that is simultaneously achieving several competing objectives, and you express each objective as a constraint on a different transfer function from the closed loop system. The sensitivity function S, it describes how the output error responds to disturbances. Like making S small means the system rejects disturbance as well. The complementary sensitivity function T, that describes how the output responds to reference commands. Making T small at high frequencies means the controller does not amplify measurement noise. So the control effort transfer function Ks describes how hard the controller works. Making Ks small means the controller uses gentle inputs and it doesn't wear out actuators. So these objectives conflict with each other in ways that are well understood. For example, good disturbance rejection requires high controller gain at low frequencies, which means that S is small at low frequencies. But high controller gain at high frequencies amplifies noise and can excite unmodeled dynamics, so T must be small at high frequencies. The mixed sensitivity design chooses weighting functions for each objective and then finds the controller that minimizes the worst case combinations of all three, measured in the H-infinity norm. That's the maximum gain across all frequencies. Now the master law framework augments this standard synthesis with additional penalty terms that explicitly account for the identification, uncertainty, and the truncation costs. A controller that achieves excellent nominal performance but requires precise knowledge of the plant is not robust. If the actual plant differs from the model, the performance is going to degrade. So by penalizing uncertainty amplifying designs during the synthesis, the framework builds controllers that are inherently conservative in directions of large uncertainty and more aggressive where the model is reliable. One of the deepest tools in robust control is passivity theory. A passive system is one that can only absorb energy. It never creates energy. Every input of energy results in a corresponding output or storage, with none generating internally. No energy is generated internally in the system. Passive systems have a remarkable stability property. You can interconnect any collection of passive subsystems in essentially any way, and the result will always be stable. This is because energy is a Lyapunov function for the interconnected system. The total stored energy can only decrease or stay consistent. It can never grow without bound. So it's always going to be settling, right, to a lower energy state. The Port-Hamiltonian structure of the master law, it guarantees passivity of the reduced model when the dissipation matrix lambda r is positive semi-definite, and when the conservative matrix J sub r is skew symmetric. And these are exactly the constraints that the convex projection step enforces when the operators are learned from data. So as a result, any controller designed within the master law framework, it can take advantage of the passivity-based stability arguments. Interconnecting the controller with the plant preserves the energy dissipation properties, and the stability is going to be guaranteed by the physics rather than just by some numerical verifications. So I'm going to scroll down in chapter 8, and you can look at the mathematics here. So go down to number 5, the algorithms. Going down to number 8, Monte Carlo draws. And going down to number 10, the solver numerical recommendations, and then we're down here into our code, which we're going to skip as we customarily do. Let's move to chapter 9. Chapter 9 is balanced models for control. So we're talking about finding the modes that matter for the input and output behavior here. Because when we reduce a model by keeping the modes that carry the most energy, as the SVD-based methods in earlier chapters do, what we're doing is making a bet. We're betting that the high energy modes are the most important ones for control. And the bet is often correct, but it's not always correct. Because a mode can carry a lot of energy while at the same time still being completely unobservable from the sensors, or maybe completely uncontrollable from the actuators. Such a mode, no matter how energetic it is, it's going to be irrelevant to the control problem, and you can't sense it, you can't actuate it, and it will not appear in any input-output measurement. So keeping it in the model is just wasting computational resources, and it's potentially introducing numerical problems. So how do you find the modes that matter, right? That's the question here, the balanced modes for controlling. Now conversely, a mode might carry very little energy in the free dynamics of the system. It might be naturally strongly damped, and it might always be small, but it might respond very sensitively to the specific inputs that the actuators are applying, and it might be highly visible to specific sensors in use. And this mode is crucial for control, even though it would be discarded by a pure energy-based truncation. So what balanced model reduction does is it solves this mismatch by finding modes that are simultaneously both controllable and at the same time observable. These would be modes that respond strongly to inputs and that are clearly visible in the outputs. The resulting reduced model is optimal for input-output purposes because it captures the dynamics that matter for the control problem, and it discards the dynamics that, from the controller's perspective, might as well not exist. So the key mathematical objects in balanced reduction are the controllability grommeans and the observability grommeans. Now, the controllability grommeans describe the average energy that can be deposited in each direction of state space by white noise input signals that pass through the system. Directions with large controllability grommien eigenvalues are easy to excite. The inputs have a strong effect there, but directions with small eigenvalues are hard to reach, and the inputs are going to barely touch those. The observability grommien describes the reverse. How much energy in each direction of the state space is visible in the output over time. Directions with large observability grommien eigenvalues, they contribute strongly to the measured output, and directions with small eigenvalues are nearly invisible, so the sensors barely detect them, and it doesn't matter how large the state is in those directions. Both grommiens are computed from the linearized reduced operators that emerged from the master law pipeline, the state matrix, input matrix, output matrix. They satisfy algebraic Lyapunov equations, which are linear equations in the grommien matrices. So solving these equations is the first step in balanced reduction. The Hankel singular values of a system are the square roots of the eigenvalues of the product of the controllability and observability grommiens. A mode with a large Hankel singular value is both controllable and observable, and it's easy to excite, it's easy to see that one. But a mode with a small Hankel singular value is either hard to excite, hard to see, or both. And it is, in a very precise mathematical sense, it's just irrelevant to the input-output behavior of the system. The optimal balanced truncation, it keeps the modes with the largest Hankel singular values, and it discards everything else. So the error committed by this truncation, the difference between the full model's transfer function and the reduced model's transfer function, that error will be bounded by twice the sum of the discarded Hankel singular values. So this is a very explicit computable error bound, which means that we know for sure in advance how much accuracy that we're sacrificing for any given level of model reduction. So within the master law framework, the truncation cost is augmented with the process noise contribution. This is the additional uncertainty that results from discarding modes through which process noise enters the system. This gives a modified cost function that balances Hankel singular value information, input-output relevance, against truncation noise propagation, process noise amplification. And the optimal rank is the one that maximizes the total cost. For many real systems, the state space matrices are not known directly. All we have is input-output data, right? So the Eigensystem Realization Algorithm, or the ERA, again, Eigensystem Realization Algorithm, ERA, that is a method for constructing a balanced state space model directly from input-output measurements without ever computing the full order model. So the procedure works by assembling a large matrix of impulse response measurements. Those are the Hankel matrix. And then computing its SVD. The singular values of this matrix are exactly these systems' Hankel singular values. And the singular vectors give the balanced basis vectors. And truncating to rank R gives a balanced reduced model order R with a known error bound derived entirely from the data. Now within the master law framework, ERA is modified to account for the geometry, such that the Hankel matrix is weighted by W before the SVD is computed, and the resulting reduced operators are projected to the Port-Hamiltonian structure. The identification covariance sigma ID is computed from the uncertainty in the impulse response measurements, and the truncation cost includes both the discarded Hankel singular values and the process noise contribution. The balance reduction step is a bridge between the data-driven identification from chapters 7 through parts of chapter 9 here, and the control synthesis, which were chapters 8 and 10. After balance reduction, the control engineer has a reduced model that's of exactly the right size. It's small enough to be computationally tractable, and it's accurately representing the input-output behavior that matters for control, and it's equipped with rigorous error bounds. And our Port-Hamiltonian projection ensures that this reduced model is physically consistent. And the uncertainty budget, combining truncation costs, Hankel singular value tail sums, and identification uncertainty, that budget feeds directly into the robust control synthesis of Chapter 8, where it's used to design controllers that are appropriately cautious given what we do and do not know. So with that in mind, I'm just going to scroll down and take a look at the mathematics here. You can pause the video, of course, and read up on this if at any point as you like. And then, of course, I haven't included any of the code for the next couple of chapters yet. I've been lazy. So that just gets us right into Chapter 10 here. Data-driven control, extremium seeking, and online optimization. So it's a problem of real-time optimization without a model. That's what we're talking about. All the methods that we've discussed so far, remember the robust control, balance reduction, and DMD, SIND, they all assume that a model is identified first, and then a controller is designed based on that model. This is the standard two-phase approach, identification, then design. It sounds good, but for many real-world control problems, this two-phase approach is impractical. The system might be too complex to model accurately. The operating conditions might change continuously, so any model learned in the past just becomes quickly obsolete. The cost functions being optimized might depend on quantities that are difficult to measure directly. like the efficiency of a combustion process, or the yield of chemical reaction, or the aerodynamic drag on a vehicle, or something like that. But they can be estimated from easily available measurements. They can be estimated. In these situations, what we need is a controller that learns and optimizes simultaneously in real time without requiring a prior model. And here's where extremium seeking control comes in. It's one of the oldest, it's one of the most elegant solutions to this problem. The basic idea is very, very simple. You do not know where the optimum of your cost function is, but you can probe the system with a small series of perturbations, and you can observe how the cost function responds to those probes. If the cost function increases when you move in a direction, then you back off. If it decreases, then you continue. And over time, this probing and this responding strategy, it simply drives the system towards the optimum. So it's a very simple process, but it is very effective. The probe signal in extremium seeking is typically a small sinusoidal oscillation that's added to the nominal control input. The key word is small. The probe has to be small enough not to disrupt the system's primary operation, but it has to be large enough that its effect on the cost function is detectable above some measurement noise, right? So the frequency of the probe signal is going to matter. It's going to be very critical. It has to be chosen in a frequency band where the system responds measurably. If the probe's frequency is too high, then the system's dynamics are just going to filter it out, and the probe is not going to have any effect on the cost at all. But if it's too low, then convergence is going to be too slow. So the master law framework uses the transfer function g of j omega from chapter 8 to choose the probe frequency. See, we want a frequency where the gain from input to cost measurement is large so that the probe's signal creates a detectable response. The geometry matrix W enters in two ways. First, the probe directions, the direction in the input space along which the perturbations are applied. Those directions are chosen to be aligned with the most important directions according to W. Now, secondly is the demodulation step. That's the process of extracting the gradient estimate from the system's response to the probe, and it is also a geometry weighted so that the gradient estimate is most accurate in the directions that matter the most. So the heart of extremium seeking is this gradient estimation, inferring the gradient of the cost function from the system's response to the probe. In the simplest implementation, the system's output is multiplied by the probe signal, and it's averaged over time, and that's a process called lock-in detection or demodulation. And it's averaged to the exact component of the output that is correlated with the probe. This correlated component is approximately proportional to the gradient of the cost function with respect to the probe direction. And the uncertainty in this gradient estimate depends on several factors, such that the amplitude of the probe, the larger probes give better signal to noise but more system disruption than the averaging time, so that longer averages give better estimates but slower adaptation, and the measurement noise level and the process noise that is amplified through the system's transfer function. And the master law framework computes this uncertainty explicitly using the transfer function and the noise covariance from the identification step. The result is an identification covariance for the gradient estimate. It's a matrix that describes how uncertain the gradient direction is. So the gradient uncertainty has direct implications for the optimization step, because if the gradient estimate is very uncertain, maybe because the probe frequency happens to be in a band where the system amplifies noise heavily, or because of the averaging time is short, then the optimizer should take small cautious steps. But if the gradient estimate is reliable, of course larger steps are going to be appropriate. And the master law's uncertainty-aware optimization automatically adjusts its step size based on the gradient covariance. So we're seeing in every chapter that the master law is contributing critical power and stability to the system dynamics and our ability to truncate and to control. But one of the most important practical concerns in online optimization is safety, because unlike offline optimization, where you can verify the solution before deploying it, online optimization modifies the control input in real time based on noisy measurements. And so a bad gradient estimate could drive the system towards an unsafe operating conditions. A mechanical system could be pushed towards resonance. A chemical reactor could be driven towards an unstable equilibrium of some kind, or an aircraft could be maneuvered toward a stall, maybe. So the master law framework addresses this also with explicit safety constraints that are based on the uncertainty budget again. At each step of the online optimization, the framework computes the current total uncertainty. This is the identification uncertainty of the gradient estimate plus the truncation noise that flows through the discarded modes. If this total uncertainty exceeds a threshold, the optimizer just slows down, or it pauses. It just doesn't take a step that it can't justify based on that reliable information. So this is a principled implementation of the intuition that a cautious optimizer should be cautious when it's uncertain. The thresholds are not arbitrary safety margins, but they're derived from the physics of the system, from the noise levels, from the model reduction errors and the frequency domain properties of the plant itself. So the result is an online optimizer that is both aggressive when conditions are favorable, and it's appropriately conservative when the uncertainty is high. So it's worth pausing here to note that extremium seeking control is closely related to modern reinforcement learning, particularly the class of methods called policy gradient methods. Both approaches estimate the gradients of the performance criterion from system interactions, and then they update a policy or a control law by gradient ascent. The difference is largely one of scale and context, because extremium seeking typically operates in a continuous time scenario with carefully designed probe signals and with analytic uncertainty qualifications, but reinforcement learning typically operates in discrete time with random exploration and with statistical uncertainty estimates. But the master law framework's treatment of extremium seeking provides a principled bridge between these two communities. The identification covariance and the truncation cost formulas, they give us rigorous uncertainty quantifications that can, in principle, be used to design exploration strategies for reinforcement learning algorithms as well, probing in directions of high uncertainty, exploiting in directions where the gradient is well known. This is an active area of research at the frontier of control theory and machine learning, and the master law has contributions to make. So let's just scroll down here and give an opportunity to look at the mathematics. So go ahead and pause the video, obviously, and you can explore this at your will. But we're going to move on to Chapter 11, which is reduced order models, proper orthogonal decomposition, POD, quadrature weighted snapshots, and invariances. We have to recognize that modern engineering systems are described by mathematical models that can be staggering in complexity. You know, a high fidelity simulation of airflow over an aircraft wing, that might involve millions of spatial grid points, and each of them may have several state variables, velocity components, pressure components, temperature components, all of that evolving according to partial differential equations. So simulating this model for a single second of real time, it might require hours of computation on a supercomputer. Using this model as an internal predictor in a real-time controller, which needs to make decisions in milliseconds, it's just completely out of the question. There's no way. Now, the same computational and possibility arises in the area of climate modeling, in structural mechanics, in electromagnetics, in quantum chemistry. Dozens of other fields have the same high dynamical problem. The fundamental laws of physics, discretized on fine grids, they produce models of just enormous size, intractable. And yet, the behavior that matters for engineering purposes, the lift and drag on the wing, for example, or the average temperature of the climate, or the structural resonances of the bridge, these are often captured by a much smaller number of degrees of freedom. This is the central insight of reduced order modeling. This is complex systems. Even when described by enormous models, they often behave as if they were much simpler. The high-dimensional dynamics take place on low-dimensional manifolds, a curved surface embedded in a high-dimensional state space. And a good reduced order model is going to capture the dynamics on that manifold without tracking the countless irrelevant degrees of freedom. The most widely used approach for constructing these reduced order models is snapshot-based reduction. You run the full simulation, or you observe the real system, at a collection of representative operating conditions, recording the state at each time step, and then these recorded states are the snapshots. You then compute the SVD of the weighted snapshot matrix, the geometry-aware SVD discussed in Chapter 1, and then you keep only the leading singular vectors, and these vectors form the reduced basis. The reduction basis defines two complementary sets of bias vectors, the trial basis and the test basis, and these encode the most important directions in the high-dimensional state space. The reduced model is obtained by projecting the full equations onto these bases. Every term in the full equations is evaluated. It's multiplied by the test base vectors, and the result is a small system of equations in the coefficients of the trial bases. This is the Petrov-Galerkin projection, named after a mathematician who developed the technique in the context of finite element methods. But anyway, the geometry matrix W is going to play a critical role here, because without geometry weighting, the snapshot matrix treats all states components equally. A velocity field and a temperature field in a fluid simulation would be given equal weight, even though they might differ by many orders of magnitude in physical importance. But with geometry weighting, the SVD identifies the directions that are most important according to the physical measures encoded in W. The resulting basis is much better adapted to the problem, and it gives much more accurate reduced models for the same computational cost. So again, the master laws is yielding high value in these complex systems. Once the trial and test bases are computed, projecting the master law operators, these are the state matrix, the input matrix, the output matrix, and the noise covariance. Computing all that is straightforward. I mean, each operator is compressed by multiplication with the test basis from the left and the trial basis from the right, and the resulting reduced operators are small matrices of size R by R rather than N by N. But they do inherit the geometric structure of the full operators. In particular, if the full conservative operator is skew symmetric and the full dissipative operator is positive semi-definite, the projections of these operators onto the basis, they also satisfy these constraints as long as the basis vectors are orthonormal with respect to the W inner product. And this is the reason for the W orthonormalization step. It ensures that the projection preserves the Port-Hamiltonian structure and the associated physical properties of passivity and stability. The process noise covariance is also projected. The reduced noise covariance describes the intensity of noise in each direction of the reduced state space. This projected noise covariance is used in the truncation cost formula. It measures how much noise power enters into the reduced model through these retrained modes. The complementary quantity, this is the noise power that enters through the discarded modes, contributes to the truncation cost, and it inflates the uncertainty budget. So let's revisit the truncation cost. The truncation cost formula in this chapter is the most explicit and the most complete version in the entire framework, and it combines two contributions. It uses the signal energy and the discarded modes, measured by the Hankel singular values of the balanced reduced models as discussed in Chapter 9, and the process noise that flows through the discarded modes. The second contribution is the novel one. In classical model reduction, the only cost of truncation is the approximation error, the signal in the discarded modes that the reduced model ignores. But in the presence of process noise, which is always present in real systems, there is an additional cost. The noise that enters through the discarded modes is not just ignored, it's unaccounted for. From the perspective of the reduced model, this noise appears as an unexplained residual, which inflates the prediction errors and it degrades the controller's performance. But by explicitly computing the truncation noise cost and including it in the total cost function for the model order selection, the master law framework ensures that the optimal rank accounts for both approximation quality and noise amplification. And this in turn leads to reduced models that are better calibrated as probabilistic predictors, not just more accurate on average, but more accurately uncertain. Now, when should we trust a reduced model? A recurring theme in the master law framework is the question of when to trust the model, because reduced order models are always approximate, they're always committing some truncation error, and they always propagate some process noise through their trained modes. So the question is not whether they're wrong, because they are always wrong. The question is whether they're wrong in ways that matter for the task that's important to us. But the master law framework answers this question with the same uncertainty budget. Given the current values of the truncation cost and given the identification uncertainty, the framework can compute a bound on how far the reduced model's predictions can deviate from the truth. If this bound is small relative to the performance requirements of the control problem, then the reduced model is going to be trustworthy. But if it's large, then additional model reduction modes should be retrained, or the model should be identified from more data, or the controller should be designed with more conservatism. Anyway, this is the fundamental promise of the master law framework. Not that the models are perfect, but that their imperfection is quantified, it's tracked, and it's accounted for at every stage of the pipeline, from identification all the way through to control. So let's take a minute and look at the mathematics of Chapter 11 here, and then we'll be able to jump straight to Chapter 12 and finish this our conversation. Now just go ahead and pause at any point in the video, and just if you feel like reading through this, that's fine. So here's our last chapter, interpolation. Interpolation for parametric reduced order models and ROM libraries. So we want to build these adaptive digital twins that learn and that evolve. That's what we're doing. And the problem we're facing is this parametric uncertainty again. Until now, the master law framework has focused on building reduced order models for a single operating condition, maybe a particular temperature, particular pressure, a speed, some load. But the real world is almost never locked into a single operating condition, is it? Like at that aircraft wing, it experiences different speeds at different altitudes, different angles of attack. A chemical reactor is going to run at different temperatures and different feed rates. A power grid operates across different seasons, different times of day. There are varying demand patterns that are on it. A patient's cardiovascular system, it changes when they exercise, when they take medication, when the disease progresses. In each of these cases, and many more obviously, the underlying physics, the laws that govern the system, they all remain the same, but the specific behavior of the system is changing dramatically with the operating parameters. A wing generates lift through the same principles of fluid mechanics, whether it's flying at 200 miles an hour or 500 miles an hour, right? But the relationship between the angle of attack and the lift is fundamentally different at these two speeds. Similarly, a reactor's chemistry follows the same reaction mechanisms, whether it's running at 50 degrees Celsius or 150 degrees Celsius, but the rates of reaction are exponentially different at those temperature differentials. So a naive approach would be just to build a separate reduced order model for each possible operating condition. You just collect snapshots at speed 200, you build a reduced model, and then you collect snapshots at speed 300 and you build another reduced model, and then you do it at 400 again, and then at runtime, when the system is operating at speed 350, you either pick the nearest model or you frantically recompute one before you crash. Anyway, the approach is computationally wasteful, it's memory intensive, it's fragile, and it also ignores a very crucial insight. The low-dimensional structure of the system probably doesn't change dramatically between nearby operating conditions. The basis that worked well at speed 300 is probably not fundamentally different from the basis that works well at 350. So parametric reduced order model libraries, they address this problem by building a collection of reduced models sampled across the space of operating parameters, and then using interpolation to construct a reduced model for any parameter value in between or even slightly beyond the sample points. And this is really the essence of Chapter 12 here. learning how the structure of a complex system changes with its operating parameters, and then using that learned structure to make predictions at new operating conditions without having to recompute the entire model. And the first step in building a parametric reduced order model library, the first step is to choose representative operating conditions across the parameter space of interest. So if we go back to our aircraft, if you're modeling the wing of that aircraft and the relevant parameters are speed and angle of attack maybe, then you might choose a grid of speeds from 200, 250, 300, 350, 400, 450, 500 miles per hour, and then angles of attack from -5 degrees to +15 degrees, and you might sample at every 5 degrees. And that is a 7x5 grid, so you'd have 35 operating points, and for each grid point you run the full simulation, or you collect data from the real system and then record the snapshots. So you now have a reduced order model library, you see. Now the choice of a sampling grid is actually a kind of careful balance. More samples mean more computational cost up front, but better convergence of the parameter space and more accurate interpolation later. But fewer samples mean lower upfront cost, but it means also coarser coverage. So in practice, adaptive sampling is often used. That's where you start with a coarse grid, you build the interpolation, and then you add more samples in regions where the interpolation error is large or where the parameter space is densely populated with operating conditions of interest. So you take a coarse sample and then you fill in where you need to. You don't fill in everywhere. Now the samples can also be arranged in different ways. A grid is conceptually simple and it works well if the behavior of the system changes smoothly with the parameters. But an adaptive or nested grid, where samples are added recursively in regions of high error, this is more effective if the system behavior is smoother in some directions than it is in other directions. A randomly perturbed or a Latin hypercube design avoids the curse of dimensionality while dealing with higher dimensional parameter spaces. And the master law framework is agnostic to these choices. The key requirement is that the samples are selected deliberately and that their coverage is tracked so that their interpolation outside the sample region can be flagged as uncertain by the master law. For each sample point in the parameter grid, the process that has been described there in chapters 1 through 11 is executed, the entire process. You collect the snapshots, you compute the weighted SVD, project the operators, enforce the Port-Hamiltonian structure through convex optimization, then you compute the uncertainty metrics. The result is a local reduced model. It's a small system that accurately captures the dynamics at that operating point. But the local reduced models are not independent. The reduced basis vectors, these are the directions that matter most at one operating point, they often overlap significantly with the reduced basis vectors at nearby operating points. So if you plot the basis vectors at successive grid points, and then they're typically going to evolve smoothly, they're going to rotate gradually as the parameter changes. And that smoothness is exactly what makes parametric interpolation possible. It's just that there's some continuity in the underlying physics, you see. So for each sample point, the local model includes the trial basis vectors, denoted as V in this framework, and the test basis vectors, denoted as W, and the projected operators, the conservative operator J, the dissipative operator lambda, and the input matrix B, and the output matrix C, and the process noise covariance. It also includes the uncertainty metrics, the identification covariance, a sigma ID, which quantifies the uncertainty in fitting the model to the data, and the truncation cost, which quantifies the information that's been discarded when we're reducing the model order. Storing all of these ingredients for each sample point in the parameter space is the ROM library, the Reduced Order Model Library. It's a collection of local models that, again, collectively cover the operating regime of interest. So for a moderately sized parameter space, say 2 to 5 parameters with 5 to 10 samples per parameter, the reduced order model library, it might contain as low as 25, even up to as high as 100,000 local models. For a 4 parameter space with 8 samples per parameter, that's 4,096 local models. The memory cost is not trivial, but it is orders of magnitude smaller than storing the fully high-dimensional snapshots or trying to maintain full resolution models at each grid point. Let's talk about the interpolation operator space, because once the ROM library is populated, the central question is, how do you build a model at an arbitrary parameter value that was not in the original grid? The naive approach, again, is to interpolate the space of reduced bases. You find a few nearest sample points in parameter space, and you interpolate their basis vectors using standard techniques like barycentric weighting or radial basis functions. The result is an interpolated basis, which you can then use to project the full model or to construct a reduced model directly. But there is a subtle risk here. Base vectors are not numbers. They're directions in high-dimensional space. That's what they really are. So interpolating two-direction vectors component-wise, like you would interpolate a set of two numbers, it doesn't in general produce another valid direction vector, does it? If you average two unit norm vectors, the result is typically not a unit vector. More perniciously, if you average the basis vectors from two different operating points, the resulting vectors are not necessarily orthonormal with respect to each other. I mean, even if the original basis vectors were. So the master law framework sidesteps this problem by working not with the basis vectors directly, but with the operators that they define. Because when you project the full model operators onto a reduced basis, you obtain the conservative operator J sub r. You obtain the dissipation operator lambda r, also the input matrix B sub r, and so on and so on. And these operators are matrices. They're numerical objects that can be interpolated by ordinary component-wise averaging. So after interpolation, you just enforce the structural constraints that the operators have to satisfy. J sub r must be Q symmetric, lambda sub r must be positive semi-definite, and so on and so on. So this is a principled and computationally efficient approach. You interpolate each operator independently using barycentric weights or other smooth interpolation schemes. And for the conservative operator, you just average the skew-symmetric matrices from the nearby sample points. And for a dissipation operator, you average the positive semi-definite matrices, and then for input-output and noise matrices, you just simply average those. But the result is a small collection of interpolated operators. So again, the master law is becoming more and more of a critical central player in a large system here. But now comes the critical step. The interpolated operators, they don't automatically satisfy the Port-Hamiltonian constraints. The interpolated conservative operator might not be perfectly skew-symmetric, because interpolating two skew-symmetric matrices component-wise should yield a skew-symmetric matrix, but numerical errors and the discrete nature of the interpolation scheme, they can introduce small violations. The interpolated dissipation operator might have small negative eigenvalues, and of course that would violate positive semi-definiteness. So these violations are going to typically be small. They're going to be on the order of numerical precision or the interpolation error, but they're not zero. And in the context of feedback control or energy-based stability analysis, even small violations can matter in the long term. So a control law derived from dissipative systems is guaranteed to stabilize it. Derive the control law from a system that is nominally dissipative, but actually has some negative dampening, and the resulting controller might destabilize the system. The solution for this is to project the interpolated operators back onto the feasible set of Port-Hamiltonian operators. You do this using convex optimization, exactly as described in Chapter 0, and exactly as we've been using throughout all of the chapters up until now. You simply solve a constrained least squares problem. Find a skew-symmetric matrix and a positive semi-definite matrix that are as close as possible to the interpolated operators, while at the same time satisfying the structural constraints. The projection step is computationally cheap. It involves just solving a small optimization problem on a small matrix, and it will guarantee that the resulting operators will satisfy the Port-Hamiltonian structure exactly. So the projection also produces a residual. This is a measure of how far the interpolated operators were from the feasible set. If this residual is large, it indicates that the local models at the sample points are not changing smoothly with the parameters, or it might indicate that the interpolation order is just too low. But a large residual might signal that some additional samples should be added to the ROM library, or that the parameter space should be decomposed into subregions with separate libraries or something. One of the most novel aspects of the master law framework is that it does not just propagate the reduced models through interpolation, it also propagates the uncertainty. The identification covariance, sigma ID, at each local model quantifies the uncertainty in fitting that model to data. So when you interpolate between two local models, you're also interpolating between two different identification uncertainties. The interpolation rule is simple. The uncertainty at the interpolation point is a weighted average of the uncertainties at the sample points, with the same weights used for interpolating the operators. This will ensure that the uncertainty estimates remain consistent with the geometry of the interpolation. And if you interpolate exactly between two local models, like at the midpoint of the parameter space between them, then the interpolated uncertainties is exactly the average of the two local uncertainties. And if you extrapolate between the same points, the interpolated uncertainty increases as the extrapolation distance increases, reflecting the fact that you are moving away from the data on which the model was trained. So these are signals that are predictable and understandable to us. Now the same principle is going to apply to the truncation cost, the measure of information discarded by reducing the model order. Now, as you move in parameter space, the truncation cost changes at some operating points. The first 5 modes of the system, maybe they're going to capture 99% of the energy, while at other operating points, you might need 10 modes to achieve the same coverage. But interpolating the truncation cost still ensures that the uncertainty budget at any operating point accounts for both the truncation error and the identification error in a consistent, measurable, dependable way. A crucial feature of the master law is that it quantifies not just the model and its predictions, but also the confidence in the model. When you interpolate to a new operating point, the framework automatically computes an interpolation warning. How far is the operating point from the sample grid? How smooth is the behavior of the system in that region? Is the interpolation error likely to be small or large? The warning is based on several factors. The distance in parameter space from the new point to the nearest sample points. If you're interpolating in the middle of the grid, confidence is high. If you're extrapolating far beyond the boundary of the sample points, confidence is low. The magnitude of the projection residual when enforcing Port Hamiltonian constraints. If the interpolated operators are far from satisfying the structural constraints, it suggests the local models are not smoothly related. The magnitude of the identification uncertainty and the truncation cost. If they're already large at the sample points, interpolation will only increase the uncertainty. So in an adaptive system then, maybe a controller running on a digital twin, these warnings can be used to trigger active learning. If the system enters a region of parameter space where their ROM library has low confidence, the system can take action. Maybe it can run a quick high-fidelity simulation to collect new snapshots, or rebuild the local reduced models in that region, and it can update the ROM library this way. So this turns the ROM library from a static object built once during the system's development into a living resource. It's like a learning system that grows and it evolves as the system encounters new operating conditions. The master law makes this possible. Assembling parametric controllers, then one of the most powerful applications of parametric ROM libraries is in building parametric controllers. These are feedback laws that change with the operating parameters. Now, traditional control designs, they build a single feedback law for a nominal operating point, and they hope it works well across a wide range of operating conditions. And if the system operates far from the normal point, the feedback law might be ineffective, or it might even destabilize the system. with a parametric ROM library, you can design a different feedback law for each operating point. For the aircraft wing example, you build a controller at each grid point in the speed angle of attack space. Then at runtime, as the aircraft changes speed and altitude, you interpolate the controller gains at each instant. You compute where the aircraft is at the speed angle of attack. You find the nearby grid points and interpolate the controller gains between them, and then you apply the interpolated gains to the current state measurement. The interpolation procedure for the controller is the same as for the model. You work in operator space. You interpolate the controller gains, and then you enforce any structural constraints that the controller has to satisfy. For a controller derived from a Port Hamiltonian model, the structure constraints, they ensure that the closed loop system remains dissipative and stable even after interpolation. And this approach is fundamentally more robust than gain scheduling in classical control theory because it's built on reduced models that accurately capture the changing dynamics of the system across the entire parameter space. And it's also more computationally efficient than online optimization because the controller gains are computed offline and they're stored in the ROM library. Now, we could go on and on. There are so many real-world applications. There's so many ways to integrate with data-driven machine learning methods. There's many computational trade-offs with memory that you can do. There are some challenges and there's some limitations. There's also the vision of parametric digital twins. And the master law opens up a lot of possibility, but we won't talk at length about all that here. I'm just going to say that we've opened up a new Pandora's box of possibilities here, and we'll leave it at that.